Good evening everyone, I'm Shubham Agarwal. Today I'll be presenting our work on approximate caching for efficient serving of text-to-image diffusion models. This work is done in collaboration with my colleagues from Adobe Research as well as one of my past colleagues who is now at UIUC. So before we dive into the details of our work, let's first try to understand the scale of image generative AI. According to a recent survey, AI has already generated over 15 billion images by August last year, which is equivalent to the collective output of photographers worldwide over the past 150 years. Moreover, enterprise solutions like Adobe Firefly, DALL-E, and Midjourney have witnessed a surge in their user base. These platforms are increasingly being integrated into various creative applications, ranging from text art generation to creating cartoons and art forms, and even extending to enterprise use cases such as flyer and template generation. This surge is particularly fueled by the natural language interface-driven generation capabilities, along with the fine-grained control over the generated content that these technologies offer. As popularity increases, so does resource requirements and costs. The evolution of compute as well as the scale and complexity of generative models are evident. However, complex models demand high-end compute, creating entry barriers for users due to costs. Furthermore, model complexity often outpaces hardware evolution despite advancements in the compute. For instance, the older stable diffusion models used to take approximately 3 seconds for a single generation on V100 GPUs, while the newer, much larger models like Stable Diffusion XL requires around 6 seconds for a single generation on high-end A100 GPUs. This highlights the importance of research focusing on the efficiency of hosting text-to-image generative solutions. Diffusion models are the current state-of-the-art for image generation, so let us try to understand how it works. Diffusion model is a deep neural network that is trained to progressively denoise random Gaussian noise to generate images conditioned on text. As seen here, it operates iteratively through many hundreds of steps. These steps are known as sampling steps or time steps. The model gradually refines the image by reducing the noise levels at each iteration. However, this can take several seconds to generate just a single image. For accelerating the generation of images, previous work suggests a couple of ways to make this diffusion process efficient. The first set of work focuses on ways of approximating these 1000 sampling steps to just about 50 to 100 steps. For this, they propose various sampling optimization techniques. However, reducing it further from here without degradation is not very easy. On the other hand, the second set of work proposes to make the model smaller and computationally lighter by using traditional distillation and pruning techniques. However, it requires extensive additional training for each new base model version. Even with just 50 steps, larger models like Stable Diffusion XL can still take around 6 seconds for a single generation. Moreover, even though the distillation or pruning techniques enable efficiency, they compromise with the quality of generation for speed. We observed that these previous works overlook a very crucial aspect about these text-to-image models being served as big systems. That is, these systems are used by millions and thousands of users across multiple generations. In this work, we exploit this aspect to reduce the generation time by using a simple yet novel caching approach. The technique we propose does not require any further training and can be used out of the box for any new model. One can directly make the system efficient by simply caching the user generation for serving queries in the future. For example, we see on this slide when a new user queried for the same prompt with a dog and a cat, caching it earlier could have helped. However, this is useful only when different users query exactly the same prompt over time. But is that really the case? To understand this, we do some analysis of real user prompt logs to see how similar user prompts are actually over time. For one of these analyses, we cluster similar prompts within a time period together and check the longevity of these prompt clusters over days. We repeat this experiment for different clusters by relaxing the threshold on the similarity level of prompts allowed within each cluster. In the top left plot, where the clusters were formed for prompts that are very similar or close to being exact, we observe that the clusters fail to exist even in just 2 to 3 days. This indicates that the users actually use the generative tools for very custom generation which fail to repeat exactly across users over time. However, interestingly, as we loosen this similarity threshold and allow the clusters to have slightly more heterogeneous prompts, the longevity of these clusters rises significantly. This strongly indicates that even though prompt specifics might be different in the generative use case, but still they share a good amount of overall similarity across time and across different users. Now we know that although exact same prompts might not be queried over and over again, but similar prompts often occur over time. Keeping this in view, we propose an efficient approximate-caching technique. To understand this, let us revisit the diffusion process once again. If we observe how the iterative generation happens through diffusion, we will notice that different aspects of the image gradually occur and form across time steps. Some of these aspects like color, layout, etc. gets reasonably apparent in the generation only after a certain number of steps, after which they look more or less fixed. If we look at the intermediate generation for a couple of very different prompts, we see that the generation still looks quite similar during the initial steps. As we see in this example, the beginning steps looks very similar for all the three prompts. However, as the generation continues, we keep on getting smaller and smaller clusters which look similar. Notably, we can also conclude here that the noise from one of these can be potentially reused for generation of image for the other prompt. So we use this idea to cache the intermediate steps during generation, which can be used for bypassing the initial steps in future generations. For this system, a clear incentive is now to skip as many steps as possible. We define the skip steps as k. However, there is a nuance here that the skipping should be done in a way so that it doesn't compromise the quality. Hence, for any new incoming prompt, a set of these intermediate noises generated by the system for past prompts can be potentially used at different k's. We call this hit rate at k. The hit rate is high at lower k as everything looks very similar in the beginning, and the hit rate decreases as k increases. Thus, the system needs to decide which past prompt should be used and with what k for a new prompt. For this, we need an algorithm to obtain a sweet spot where both the quality of generation is maintained and the savings are high. For this, we now design a cache selection mechanism. So let us see this example. Here we use the intermediate noise from the image where a brown horse is grazing in a green field. We use the noise at different k's for a set of new prompts which are different in certain aspects from this cache prompt. We observe that depending on how similar the cache and the query prompts are, certain maximum k works, beyond which the model fails to generate coherent images. For example, white horse generates till k is equals to 10 and fails beyond that. However, a bear can be formed till k is equals to 20. This draws the connection between how the skip steps or k depends on the similarity of the query and the cache prompts. If they represent images that are similar enough, a large number of steps can be skipped without any quality compromise. Now, using this idea, we design a heuristic that allows us to determine k in terms of similarity score. For this, we profile the generation quality for a set of prompts using cache across different similarity levels for all k's. We observe in the middle plot how well the quality score correlates with the similarity and allows a higher k to be skipped when the similarity is higher, while maintaining the same quality. We use this to determine a mapping function from similarity score of prompt with its cache to the maximum k steps that can be skipped. Next, since we need to store the intermediate noises as cache, we need to manage the storage for this cache. So whenever a new prompt comes which cannot find any match, we simply extract all the intermediate states during the generation and insert it into the cache, if there is enough space in the storage. However, when the storage gets full, we need a policy to decide which items should be evicted in order to allow fresh insertions. Unlike most caching logics explored in the literature, our objective here is not just having a higher cache hit rate, but to have a higher compute savings primarily, which is inferred by the higher skip steps or k. Hence, we design an eviction policy by modifying the frequency-based policy where we score an item stored in the cache using a value computed by multiplying the frequency of access with the savings or the skip steps k. We call this policy LCBFU. Here in this example, we see how the top left item was evicted instead of the one at the bottom right, even though the frequency of use for the former is more, but the overall score is higher for the latter one as it can give more compute savings. We also evaluate this policy where we find the compute savings as we increase the cache size. We observe that the policy gives higher compute savings as compared to other standard caching techniques by taking into account this compute savings factor. With these two components in mind, that is the cache selector and the cache management LCBFU policy, let us now go over the end-to-end pipeline for our proposed system, which we call NIRVANA. When a new prompt comes to the system, first of all, its corresponding clip embedding is generated. Here, we use clip embedding as it allows to capture the visual semantics of the prompt, which is crucial for this use case. Then this embedding is used to search for similar past prompts in the cache. To facilitate a fast search over the cache, we host a vector database server or a VDB server. This vector database server maintains an indexing for the past cache prompts using their clip embeddings and allow efficient search using approximate nearest neighbor approach. For an incoming prompt, it finally returns the most similar cache along with its similarity score. It also returns a pointer to the actual file path where the noise files are stored in the storage file system. Now, using this similarity score, the cache selector can determine the number of steps it should skip or k, and it makes a fetch call to retrieve the kth noise file from the elastic file storage or EFS. This noise file is then used to generate the final image by skipping the initial k steps. In case when there is no match that is found, the image is generated starting from random Gaussian noise, and the LCBFU cache management policy then performs the necessary bookkeeping by using the intermediate steps generated during the diffusion for updating the vector database as well as the EFS. Now, since this process involves using the vector database to search for incoming prompts, it might be seen as an overhead for cases where no similar prompt is found in the cache, or generally speaking, a cache miss situation. Similar to our motivation, Bloom filters are popularly used as a low-cost mechanism to check cache entries by using a hashing algorithm. However, it is not suitable for NIRVANA, as in this case, we do not search for an exact match always, but we search for nearest neighbors. So to reduce the overhead, we introduce a match predictor component, which uses a one-class SVM classifier. It's like an anomaly detection system. So this match predictor predicts if there is any similar prompt that exists within the cache or not. This helps to avoid making network calls to the vector database for cases which are most likely going to be cache misses. Having gone through all the details of what approximate caching does, let us now see a few samples generated by the system for real user prompts. Here, we see the incoming prompts on the top in red. The nearest neighbor prompt retrieved from the vector database is shown in blue, referred to as the cached prompts. At the bottom of the slide, we show the image generated in the past using these cached prompts. Finally, we see the image generated using intermediate noise from these cached prompts for the incoming prompts for different skip steps or k depending on the similarity level. Here we use SDXL model and the total number of steps is 50. We see that for the last two prompts, we can have a compute saving of around 40% by skipping 20 steps. This is possible because the new prompt and the old prompt are similar enough. However, we also see that for the first three examples, when the prompts are relatively very different, still a lower k of around 10 to 15 can be skipped, and it can provide 20 to 30% savings. After this brief quality check, let us now go over some of the quantitative results. We evaluated the image generation quality of our system NIRVANA and compared it against other image retrieval techniques as well as the full diffusion model, which we refer to as the vanilla approach here. We evaluated using FID score, which lower is better, and through clip score and pick score, which higher are better. The first FID score quantifies the difference between two image distributions, while the latter two scores quantify the coherence and the user preference of an image generated for a given prompt respectively. We see that for two real-world prompt traces, NIRVANA outperforms all the other retrieval techniques and scores very similar to the Oracle scores obtained by the vanilla approach. To further validate the generation quality, we also conducted a user survey where we provided users with prompts and the image generated using either of the three techniques, GPT cache, which is a state-of-the-art retrieval technique, our system NIRVANA, as well as vanilla diffusion model. We ask user a yes-no question for if they think the image properly represents the prompt. As a result of this user study, we found that the acceptance rate of NIRVANA is around 79%, which is very much comparable to the vanilla diffusion approach, and it significantly surpasses the GPT cache approach, which has just an 31% acceptance rate. Next, we evaluate NIRVANA on a couple of system performance aspects. We analyze the throughput obtained by NIRVANA and compare it with respect to the vanilla deployment of diffusion model. We observe that NIRVANA attains about 1.25 times improved speedup in terms of average system throughput as compared to the vanilla approach. We also do a cost analysis of the system to understand how do the additional overheads contribute to the overall cost. we find that NIRVANA is able to reduce overall costs by around 20%. This is attributed to the higher system throughput and hence lower GPU cost per image, which is attained by NIRVANA. Notably, despite the slight overheads introduced by the storage and the indexing components, that is the vector database and the EFS, overall costs are significantly reduced as GPU costs cover a significant proportion of the overall costs. We also do a list of other evaluations and ablation studies with different embedding type, caching policies, etc. Please refer to the paper for more details about the same. Finally, I would like to conclude by summarizing the presentation today. NIRVANA is an approximate caching technique for diffusion models, where the main idea is to cache and reuse intermediate noise states from across generations. Here, the cache is selected by balancing the trade-off between compute savings and quality. Also, the cache storage is maintained through a unique novel eviction technique that is optimized for higher compute savings. We finally evaluate NIRVANA on 2 real-world prompt logs and observe that NIRVANA enables image generation at a higher system throughput and lower cost with minimal quality difference. For more details, please check out our paper on the first link. Also at Adobe, we are working on many more such cool stuff which you can check out here on the second link. Thank you.